So when we're looking at nuclear reactions, the last part we're going to look at is artificial transmutation. But before we do that, I just want you to remember what changes with a nuclear reaction and why do we call it nuclear. So we need to focus that nuclear focuses on the premise of the nucleus and the number of protons and neutrons in the nucleus. So that's what changes in the atom with a nuclear reaction. So remember that transmutation can either be natural, which means spontaneous, or artificial, which is what we're going to focus on in this video. Remember, natural transmutation is spontaneous. It's either an alpha decay, beta decay, or a positron emission. And we use table O when dealing with natural transmutations. So the opposite of natural transmutation is obviously the artificial transmutations. And artificial transmutations is when humans cause a change in the nucleus by smashing atoms or particles together. By doing this, we're releasing very, very large amounts of energy. The two types of artificial transmutation we have is fission, which sounds like division, and that's exactly what's taking place, is that a neutron smashes into a large atom, producing smaller atoms and neutrons, and as a result of that, causes a chain reaction. So now the neutrons produced then go and smash into more atoms, and so on, and so on, and so on. Each one of those collisions produces a great amount of power, and by doing so, you're creating an overall net system of a lot of energy. And this little diagram over here shows you the incident neutron, and then the dividing nucleus, and then the releasing of those other neutrons. And as it releases those other neutrons, then they bombard into other nuclei, causing that chain reaction. And what the byproduct and the problem with fission is that you produce a lot of harmful isotopes. Fission is one of the common ways that we use, or are actually starting to decrease of use of nuclear power. So in this given expression, you can see uranium's bombarded with a neutron in the nucleus, and then it produces two byproducts, but also this 3 neutrons here, which is why you can really key in on this being fission. As you divided one nuclei, or actually in this case a whole atom, and then since you took that atom and you now divided it, and you're releasing these 3 neutrons. The opposite of fission is just the opposite in life. Fission is to divide, fusion is to put together. Easiest way is looking at this statement here. You can see that I have 2 different hydrogen isotopes producing a helium atom, plus a lot of energy. So 2 small isotopes fuse into a larger atom. Usually it's hydrogen producing helium. One of the nice things about fusion is you do produce a lot of energy. There's no dangerous byproducts. However, it can't be done at efficient temperatures. We cannot harness this amount of energy. Fission we can, using a couple different methods in nuclear power plants. However, with fusion, we have not been able to harness this types of energy. Examples and common uses of some radioisotopes that we is detection and treatment of diseases, radioactive dating of fossils and geological structures. We also use them in industrial chemistry and tracing biological or chemical processes. So we do use these radioisotopes quite often in science because they do have uses, especially if a known literature half-life value is known, so then you can tell how long something's been there for. Also, the last part there is medicine. We do use some of these radioisotopes to involve as a way of treatment, but also as a form of medicine as well. Some specific common radioisotopes that are used is I-131. Okay, so iodine-131 we use in diagnosing and treating of thyroid disorder. Easiest way to remember that one is thyroid, I as iodine. Carbon dating, carbon-14 to carbon-12, uranium-238 to lead-206 for geological structures. Cobalt-60, treating for some forms of cancer. And those are all the common uses that New York State likes to have you know. So it's always good to know these, and you will be assessed on your exam for those. So that wraps up nuclear chemistry. We looked at natural transmutation versus artificial transmutation and the different ways that nuclei break down, producing different types of isotopes. Remember, the most important thing with dealing with any unit, but this unit in particular, is the law of conservation of mass, showing that your atomic mass is conserved along with your atomic number.